Hello everyone, in this video I want to review some Sage Math for you from the week 8 and which we have done the week 8 tutorials almost about 3 weeks ago. I want to review some Sage Math for you, although we have uploaded the PDF of this Sage Math in the Blackboard. Now let's start with the question 1, and I have uploaded the same PDF. I just want to explain some as review for you, therefore probably you will be able to understand better. Now the question 1 says solve the question the differential equation y prime equal to the y times x minus 2 with this initial condition. So we know that the algorithm, if we want to use that, we just need to have a function and a loop for iterations, and if we want to find the target value for y, we have to follow the Euler's algorithm. Now I have the x initial in my inputs, and the y initial, the step size, and the y target for, so I have to put my x target here, then I have to find the corresponding y for that. So here I calculate that how many iterations I need to do this loop, and here I have y target equal to the y0 or y initial plus y initial times or f of xy times h, and after finding this y target, I will assign it this new y target to y initial y, and also one step, I will add one step for x initial. Then I will do this loop, so at the end I want the computer to return me y target. So here I can call my new just built function here. The initial condition was x equals 0, y equals 1, and the step size 0.2, and I want to calculate 0.4. Means I want to know that the solution when the x is equal to 0.4, and this is my solution, and I can do with smaller step size 0.1, therefore I will get this answer. Now if I want to know that with how speed the computer or the Sage Math or Python do this calculation for me, I have to call the time model in Python or Sage Math for myself, and I have to measure the time of for this calculation. After shift enter here, and I get this number per second. And now let's use the Euler method, which is a function inside of the Sage Math, and therefore I have to firstly define the variables x, y in this way. I will explain this later. And here I will get this solution. So the last solution, you see that this one, and which is compatible with this one. So this is the f of xy initial condition, step size, and the target for x. And if I want to use the time for this, if I want to know that how much does it last to calculate this, I can use the same thing for this here, and therefore I will get this number which is more than or bigger than this number here. Therefore we can see that the algorithm, our own algorithm here, is faster than the function which is built inside SageMath. Now here you can see that this number is not in the same column, so what I can do is just put 0.0 here, and therefore the SageMath will not assume that these 0 and 1 is they are not like in the format of integer, so I will get almost in a regular way. Now here in question 2 I have this SageMath here, and I want to solve the Euler methods for this function y prime equal to the f of xy equal to the 2xy with this initial condition. So you can see that we just need to define xy as variables in this way here, and using this Euler method, the first argument is f of xy, the second argument is the initial value of the x, and the third argument is the initial value for y, then after step size, then after the target point. I mean the target, we want to calculate the y in this point 1.6. so you can see that we can from 1 up to 1.6 with step size 0.2 we will have just 3 loops. Therefore when x is this number, y is, or the solution is this number. And in the same way we can make the step size smaller, therefore we have to wait more because we will have more loops. And about this, how we define the variables here, this means that xy, or in my name Hamed, is a variables of the polynomial of degree 2, which the coefficients are rational numbers. It will generate these two variables here. Python and SageMath always starting from 0. Unlike MATLAB, if you write xy, you will get xy, which is more logical. You can write your name here. I prefer to write my the variables or define the variables in a classic way, but I will get this notification here. But so in order to ignore this, we have to write in this way here, and I haven't found any logical reason for this. Now if I add this argument here, algorithm is equal to the none, then I will not see this third column here. Okay, so I will have just a list of x and y here. Therefore this xy list will be helpful in plotting. So in question 3 says that plot the solution of the previous ODE, means this one here, using Euler's method. You can see that here xy polynomial ring, we define the xy variable here, and the first ODE is this one with the step size 0.2, and the first list underline plot gives us the point here, this point here, and the line for connecting the points to each other. We have to use this function here, and the color is obvious, and this will be helpful connecting the points to each other. We don't need again to define the xy variables again. So another Euler's method for with different step size, smaller one here, and we can do the same thing here with different color. Then we can see that the solution of the ODE will be more exact. In order to see how exact it is, we can go to the question 4. Says that solve the question for this with this initial condition. So we can use DE-solve, and in order to see that how we can use DE-solve, just have a look at the previous video about which is a review about the first session of Sage Math, and we get this solution here with this initial condition. I multiplied everything by 2, then I get the square root, and I plot this one here. I get this true or exact solution for this ODE. Now I apply Euler's method with different stage, and I collect all the plots in one plot. T is the exact solution, P1 and P2 is related to the red one, and P3, P4 is related to the plot which is a green. You can see that step size is smaller. As it is smaller, it's very close to the exact solution. Now let's do the question 5. Says that plot the y prime minus sinc function times y equal to 0. It's impossible to integrate this function, therefore the Sage Math also is not smarter than us, so the DE-solve will be a numerical solution. This EI parenthesis open and close I means the sine function. You can Google it or search it in the Sage Math website. This just EI is enough to search that, and you will see that it's not an analytic function. Now having this one and doing the Euler's method for that, here you can see that Euler's method is also it looks like a exact solution. Now in question 6 says that y prime equal to the sinc function times y, and plot the direction field. So for the direction field you can use this function. Note that I didn't need to use the unusual way for defining x and y. I mean this one here. So I prefer to use the classic method for defining my variables. You see that this is the direction field. Now in the next question, or not in the next question, actually we can define y prime equal to this one, and we can solve it by Euler's method, and we can from this actually I can combine these two plots in one plot, and probably you will see the same thing in your assignment, and you can use the same similar method to solve your question. And in question 7 you can see that there are sometimes some differential equations, although they are Riccati, which is a familiar for us, but the Sage Math or especially DE-solve cannot solve this function. Therefore we need to use just numerical methods, and you can see that the plotting direction field confirms that our Euler's method is true. And this is the end of the video. I hope you guys enjoyed. I hope you will be able, this will be really useful for your second assignment.